Let the universe begin. Wait, but what if it didn't happen like that? Or not quite like that? The Big Bang Theory in its modern form is the most widely accepted description of how the universe evolved from its earliest stages. However, since I'm saying the most widely accepted, it implies that it's not the only one. There are other theories. It's just that the Big Bang Theory has been the most successful. But that's just a theory. But sometimes people confuse the concepts of a hypothesis and a theory, or just don't know what the word theory means in science. The Big Bang has its own haters. Though right now I'm more talking about lay people rather than scientists. And it's not hard to get where they are coming from. If you tell an unprepared person that once the entire universe, space and time and everything that fills it, were compressed into an unimaginably small size, and then suddenly for some reason it all started to expand, and at first it expanded very quickly, and then more slowly, a person might probably say, wait, what? Sometimes even regular people try to come up with their own alternative versions of evolution and even the origin of the universe, though they publish them not in scientific journals but on internet forums. Send letters with their ideas to cosmologists, and even I received some messages of this kind. But scientific theories, especially fundamental ones, are not some arbitrary and unsubstantiated ideas. I can also come up with something like, the Big Bang is a sneeze of some interdimensional being. Or something more elaborate with a bunch of smart-sounding words which won't immediately sound like nonsense. Nevertheless, no scientific journal would accept such an idea from me. Well, at least they shouldn't. Not because scientific journals are an elitist community that only admits its own, but because such my hypothesis would not meet the basic criteria that a real scientific theory should adhere to. The Big Bang Theory has held its ground for many decades because it successfully predicts many phenomena that we actually observe in the universe. It is currently the best explanation we have. However, in the history of science it happened many times that some widely accepted theory had become outdated and a new one took its place. Will this happen to the Big Bang Theory? We can't say no for sure. Even though it's currently the best, it doesn't mean it's perfect, and it has some problems. And attempts were made to create alternative scientific theories. So let's talk about that. About the Big Bang itself, about its problems, and most importantly, about the alternatives. My name is Andrei, and this is Cosmos Elementary. A scientific theory is popular not because it benefits someone, or it's trendy, or it simply sounds plausible. A theory must successfully explain something, and the Big Bang Theory does that. By the way, there is even a book written by astrophysicists and cosmologists Luke Barnes and Geraint Lewis, titled The Cosmic Revolutionary's Handbook, or How to Beat the Big Bang. The book meticulously details why scientists consider the Big Bang Theory to be the most successful. So in interviews, the authors of the book mentioned that there are often two polar opposite views on science. Some people idealize it, perceiving it as perfect knowledge, but others believe that science is a greedy pursuit of power by self-proclaimed experts who only want to confuse people with intelligent words and their mathematics. But it's neither one nor the other. And for those who truly want to challenge the Big Bang Theory, they need to be able to explain what the Big Bang Theory explains well. But what does it explain well? To arrive at the modern understanding of how the universe works, humanity has undergone a complex journey spanning hundreds or even thousands of years. Our views on how it's structured changed, as well as the size of the universe as we view it has consistently increased. A long time ago, people believed that the Earth was at the center of the universe, but eventually the heliocentric model prevailed. It is always striking to me how just about 100 years ago we thought that our galaxy, the Milky Way, was the entire universe. And other observed galaxies were considered nebulae within the Milky Way.
Before the discovery of the expansion of the universe, it was described as stationary, meaning not expanding. It was eternal and infinite. However, that model faced serious problems, such as emergence of some paradoxes.
For example, the famous Olbers paradox, which suggests that if the universe is infinite and stars are more or less evenly distributed, then although stars at a certain distance become dimmer, at the same time, there are more of them in the same area of the sky. One thing should compensate for the other, and according to this logic, at night we should observe not a dark sky with individual stars, but the entire sky should be filled with bright light from the infinite number of stars. Something similar should happen with gravity in such a universe. Again, in an infinite universe uniformly filled with matter, any given point should experience infinite gravitational attraction.
And a tiny little detail: if the universe is eternal, then nothing should exist. Because over an infinitely long time, everything should have achieved the state of thermodynamic equilibrium. Everything would have achieved the state of heat-death.
These paradoxes are so-called paradoxes of paradigm, meaning they existed within the views of the universe at that time. However, if we abandon the idea that the universe is eternal and stationary, these paradoxes disappear.
But one does not simply discard established views.
Even Einstein in 1917, after developing the general theory of relativity, constructed the first relativistic model of the universe, which was static. However, later he had to abandon this idea, but it took serious arguments to do so.
Usually when people talk about the discovery of the expansion of the universe, Edwin Hubble immediately comes to mind, although he was certainly not the only one who contributed to it. Hints at this, not only in the form of paradoxes and inconsistencies, but also in the form of observations and calculations, began to appear earlier.
In 1912, the American astronomer Vesta Melvin Slipher observed spiral galaxies and measured their redshifts. At that time, it was still unknown that these objects were individual galaxies. They were considered nebulae within the Milky Way.
And just in case you forgot, I'll briefly remind you about the redshift and the Doppler effect. Everyone has heard how the pitch of a sound changes, for example, from a passing train or a car.
This happens because the object is moving and the sound waves compress when it approaches us and stretch when it moves away.
And that's when we hear something like that.
The same thing happens with light waves. Only the light from approaching objects shifts to the blue part of the spectrum, to the shorter wavelengths, while the light from receding objects shifts to the red part, to longer wavelengths, hence the name redshift. By measuring this redshift, it is possible to determine that the object is moving away from us and roughly at what speed. So Vesta-Slipher measurements revealed that typically all spiral, nebulae were moving away from us, hinting at expansion. By the way, if you notice in some of Hubble's papers, they were still referred to as spiral nebulae for some time.
In 1922, Russian mathematician, physicist, and cosmologist
Alexander Friedmann developed the Friedmann's equations within the framework of Einstein's general theory of relativity.
Friedmann showed that Einstein's static universe is highly unstable, and Friedmann's model predicted that the universe is not static, but either contracting or expanding.
And then came the discoveries of Edwin Hubble. In 1924, Hubble's observations showed that the Andromeda Galaxy is too distant to be a part of the Milky Way. Although his initial distance estimates were not very accurate, he was fundamentally correct. By 1929, measuring distances to galaxies and their velocities, Hubble noticed a direct relationship between them. The farther galaxies are from us, the faster they are receding, and this is now known as Hubble's law, which again pointed to an expanding universe.
In 1927, Georges Lemaître, a Belgian astrophysicist, mathematician, cosmologist, and
a Catholic priest, arrived at conclusions similar to those of Friedmann and went further after Hubble's discoveries. In 1931, he hypothesized that since the universe is currently expanding, it must have been smaller in the past. And if we, as a thought experiment, reverse time, then at some point in the past, the entire universe would have been compressed into a single point, from which everything originated. Lemaitre is often referred to as the author of the Big Bang Theory, although the name emerged later in 1949, and the credit goes to the British astronomer Fred Hoyle. Hoyle strongly disliked the theory, and he fought against it throughout his life.
And here it's often said that he used the term Big Bang to mock the idea of an expanding universe. But perhaps that is not the case.
As I was searching for information, I came across a whole article about whether he intended to mock the theory with this name. And apparently he didn't. And he rather used this term neutrally, even though he didn't like the theory itself.
It's also interesting that the name didn't catch on right away.
If we search in the astrophysical database for the words Big Bang, we will see that papers using these words started actively appearing only in 1960s. Well, and in general, of course, the name itself is not the best, primarily because it misleads people, as there was no explosion in the conventional sense. Nevertheless, both the theory and the name are now pillars of modern cosmology.
In general, the idea seems quite simple. If I launch, for example, two balls in different directions, and then cut the beginning of the recording and show to someone like this,
based on what we have observed, taking into account the movement of the balls at the specific moment, we can reasonably confidently say where they were before that. It is similar to the universe, only instead of balls, we have galaxies, and the increase in distance is associated with the expansion of space-time itself, rather than galaxies simply flying apart in different directions. So the observed expansion of the universe forms the basis of the Big Bang Theory. From this, several conclusions can be drawn and we can make a series of predictions, which then we can try to test. And here are the main predictions of the Big Bang Theory. Firstly, the universe had a beginning. And from that moment until the present, it has been changing and evolving. The farther we peer into space, the younger we see the universe, with fewer heavy elements and less evolved structures. And in the past there had to be a moment when stars and galaxies didn't exist yet. Then, if we rewind time even further, there must have been a moment when the universe was significantly smaller and so dense and hot that stable atoms could not yet form, and radiation could not propagate freely throughout the universe. Therefore, at the moment when the universe expanded and cooled enough, light should have begun to move freely, and we should see this residual radiation everywhere in the universe.
What radiation is this, I wonder?
Also, in the early hot universe, there should have been a phase now called Big Bang nucleosynthesis, a stage during which the first chemical elements in the universe formed even before the emergence of stars. In other words, the universe should be abundant with the lightest elements in large quantities: hydrogen, helium-4, and a couple more isotopes. And in general, all of this finds confirmation in observations. We observe the early universe through telescopes, up to periods just a few 100 million years after the beginning of expansion. The predicted earliest radiation was discovered and is now known as the cosmic microwave background. Its discovery is one of the key pieces of evidence supporting the Big Bang Theory. The abundance and ratio of light elements in the universe also support the Big Bang Theory.
These are the main, but far from all, arguments and pieces of evidence.
And of course, the theory also changes over time. For example, the addition of the inflation has become crucial. Inflation is an extremely brief period at the very beginning during which the universe expanded exponentially. Additionally, it has been discovered that the universe is not only expanding, but also accelerating.
But, as I've already said, the theory certainly has its problems. Some of them might turn out to be only apparent, but others are genuine.
Some might say that the Big Bang Theory violates, well, fundamental laws of physics. How can everything come from nothing? What about the conservation of mass and energy laws and all that?
But this question arises from misunderstanding. Many think that the Big Bang Theory is about where the universe came from, but that is not the case. The Big Bang Theory doesn't describe the origin of the universe. It doesn't say where everything came from.
It describes the evolution of the universe. Moreover, the description doesn't even begin from the very start. If we rewind the history of the universe, at a certain point, there is a situation where modern laws of physics just stop working, and we simply cannot describe what happened in the very first moments of the universe's existence. At the same time, the Big Bang Theory looks very far back into the past, up to the first moments of the universe's existence, but not all the way to the very beginning. So it doesn't provide an answer to the question of where everything came from, but it does a good job of describing how everything developed from the earliest moments onward. But there are real unresolved problems that include dark matter and dark energy, which, according to modern estimates, account for a significant portion of the mass energy of the entire universe. Given this, they should play a crucial role in the evolution of the universe. However, despite the idea that dark matter and dark energy should exist, we currently have no idea what they are. To achieve a more complete understanding of the universe, these problems still need to be solved. We also still don't know why there seemingly was a little more matter than antimatter in the early stages of the universe, resulting in everything around us, including ourselves, being made of regular matter. I talked about antimatter in my video about anti-galaxies. Plus, the predicted structure of the universe on both small and large scales doesn't entirely align with what we observe. These inconsistencies could be a result of either problems with our calculations and models, an issue with the theory itself, or discrepancies in our observations. The so-called horizon problem raises the question of why, on large scales, the universe is so homogeneous and regions separated by vast distances have approximately the same temperature. Why are all areas that are not causally connected so similar? This problem is addressed by the inflationary theory. There are also issues like the problem of the cosmological constant, the shape of the universe, and others. So you can see that the theory is not perfect, but it is getting better.
One of the main competitors to the Big Bang Theory at its early stages was steady-state universe. It gained significant development in mid-20th century. You might have noticed that that is after the discovery of the expansion of the universe.
Nevertheless, some scientists were initially reluctant to accept the Big Bang Theory. Among the notable supporters of the steady-state universe was Fred Hoyle, who coined the term Big Bang.
From the name of the theory, one might think that it completely denies expansion and suggests that the universe is static. However, that is not exactly the case. The name steady state concerns the average density of matter.
In the Big Bang Theory, as space-time expands, the distance between distant objects increases, and the density of matter in the volume of space gradually decreases because, well, there is nowhere for new matter to come from, obviously. So that's what the theory of a steady-state universe is about. In this scenario, the universe is expanding in size, but the average density doesn't decrease because new matter is continually created within it. Such a universe would be eternal, infinite, and perpetually uniform. Its density and structure on large scales would remain unchanged.
Besides the obvious questions like where does that extra matter come from? The theory was essentially laid to rest by the discovery of the cosmic microwave background radiation and quasars.
Both discoveries share the commonality that the light we receive comes from the epochs when the universe was obviously very different. The cosmic microwave background originates from a time when stars had not yet formed, while quasars provide insights into an era when galaxies were much more active than they are now. So this demonstrates that, no, the universe has not always been the same.
Another alternative to standard cosmology is a so-called plasma cosmology or plasma universe.
The idea belongs to Hannes Southern, the founder of magnetothermodynamics and a Nobel laureate. If in standard cosmology on large scales everything is governed by gravity, then in plasma cosmology, electromagnetic forces play the leading role. So the logic here is that these forces are stronger than gravity, so everything we observe around us could be governed not by gravity but rather electromagnetism. This applies to all processes, from the birth of stars to the expansion of the universe.
In alpha model, the universe consisted of large clusters of matter and antimatter, and those bubbles struggled with each other and expanded, and that we observed as expansion. When they collided, radiation emerged, which we observe as CMB.
However, all of this simply doesn't correspond to what we observe, specifically the fact that the farther galaxies are, the faster they are moving away. In a plasma universe, this should not be the case. As I mentioned before, the Big Bang Theory does not provide an answer to the question of where the universe came from. So we'll look into the past until the early moments where our physics holds, and perhaps there is no need to look further. That's where the idea of a cyclic universe comes up. The universe might expand, then come to a stop, start contracting, reach minimal but not infinitesimally small size that violates the laws of physics, and then the universe bounces back, and this cycle continues forever.
Here, one might think that the question of what was before the Big Bang is addressed, because before the Big Bang, there were an infinite number of Big Bangs and contractions. Essentially, it's a version of an eternal universe. However, the question of where everything came from still remains.
For the universe to stop expanding and start contracting, the mass energy density has to exceed the critical density. Currently, modern measurements indicate that this density is very close or equal to the critical density, and it is more likely that the universe will continue to expand. However, we can't rule out the possibility that new data could potentially lead us to rethink this.
There were opinions that the Big Bang Theory is incorrect because the data it's based on were initially misinterpreted.
For example, the hypothesis of tired light. One of the main arguments in favor of the expansion of the universe is the redshift. But the tired light hypothesis suggests that the light from increasingly distant objects appears redshifted to us, not because space-time is expanding and the wavelength of light traveling through space is changing.
And that's because light, gets tired. As it travels through the universe for billions of years, it interacts with matter and loses energy.
But this is directly contradicted by many observations, and moreover, expansion is confirmed by observations of supernovae.
There are also more radical ideas.
For example, the Ekpyrotic Universe model suggests that our universe is the result of a collision between two three-dimensional brains from the fourth dimension. Brains are fundamental objects in string theory. I'm going to make a separate video on that topic. As you have noticed, this model is derived from string theory, which is itself far from perfection and experimental confirmation.
There's an idea of eternal inflation, and here we are delving into the multiverse.
In this scenario, there should exist a hypothetical inflaton field, which is in a state of constant inflation. However, in certain regions, it weakens, and there bubbles appear, expanding much more slowly. And our universe is one such a bubble. And there could be a vast number of other bubbles which we may never be able to make contact with. And in these bubbles, there might even be different laws of physics. There's also a version suggesting that we supposedly live inside a black hole, and that black holes in our universe contain other universes within them. In short, we probably don't live inside a black hole. Observations contradict that idea. Of course, this is not all. Many theories and hypotheses have their sub-theories. However, after discussing some of the main alternatives to the Big Bang Theory, I think it becomes clear why the Big Bang Theory is still considered to be the leading one. Many alternatives are directly contradicted by observations, and some can hardly be called full-fledged scientific theories, and I haven't even mentioned the simulation hypothesis. It's important to understand that no one claims that the Big Bang Theory is perfect. It has its problems. Recognizing what it explains and what it doesn't is important. In the future, it may be replaced by a better theory, or perhaps it will continue to be refined, improved, or integrated into a more complete framework. But for now, it remains the best we have.
Thanks for watching. Links to all of the sources are as always down below in the description. If you enjoyed the video, leave a like, comment, subscribe for more videos in the future, and feel free to share this video with your friends. Bye.